So for part C of this problem, we have to generalize the equation for any delta y. And we're going to work with the equation of work in function of the variation of kinetic energy. So in this problem, work is going to be, or in this work, the problem, the work is the mass of the object times the gravitational force times the variation in height, which is delta y. And the kinetic energy is 1/2 the mass of the object times the final velocity to the second. And this is the only part of the equation that we use because the initial velocity of the object is 0. So we're going to cancel out the mass because it's the same on both sides. And we are left with the following. Final velocity to the second, it's equals to the 2 that we're going to transfer to the left side of the equation, which as a 2, the 1/2. 2 times the gravity times the change in height, which will translate to the square root, or final velocity is equal to the square root of 2 times gravity times the change or the variation in height. It is important to know that delta y is always going to be positive value. For part D, we have to find the potential energy associated to the force that was applied on the object. So, we know that the work done by the object is equals to mass of the object times the gravitational force times the variation in height. So y1 minus y2, right? This will translate to the potential force applied to y1 at y1 position minus the potential force applied at y2, right? So now, from this part, we can say that the potential force at y1 is equals to the mass of the object times gravity times y1 plus c, and same thing at y2, right? It's mass times g times y2 plus c. If we combine these two equations, we can say that the potential at y1 minus the potential at y2 is going to be equals to the mass, the multiplication of the mass times gravity times y1 minus mass gravity of y2. But how do we find that potential energy? That's found by the mass of the object times gravity times the change or the variation in height, which will translate, of course, to mass of the object times gravity times y1 minus y2. Work will be the force times the distance, which basically translates to the same equation because we're talking about the gravitational force in this example. Y1 minus y2. So from previous we found before work to be 400 joules. So the gravitational force in this example will be 400 joules per kilogram. We combine this. So mechanical energy can be represented by the following equation. The total number, that's going to be the mechanical number, is constant when forces are conservative. So we can use this equation right here. K final minus K initial is going to be equals to U initial minus U final. This is the same as saying K final plus U final. It's equals to U initial plus K initial, which is 1/2 of the mass of the object times final velocity to the second plus mass gravity final position of the object, which is equals to 1/2 mass initial velocity to the second plus mass gravity initial position of the object. So given by the problem, we know that the initial velocity was 3 meters per second. The initial position is 10 meters. The final velocity is 2 meters per second. That the mass, not the final velocity, but the final position is 2 meters. The mass is 10 kilograms, but we don't know the final velocity. Now let's just plug in the values into the equation. 1/2 times 10 times final velocity to the second, which we don't know, plus 10 times 10. The final position is 2. Equal times final position is 2 equals to 1.5 times 10 times initial velocity, which is 3, plus mass of the object, which is 10. Times 10, which is gravity, times the initial position, which is 10. if we solve for final velocity, we obtain 2 points as our final velocity, which will be 13, negative 13, or 13, positive 13.